Bonsoir tout le monde et bienvenue pour cette troisième journée de la Chaos Week. On est sur le deuxième créneau de talk de la soirée. Il s'agit du talk de Yury Nino. Le sujet est le machine learning dans la prédiction du chaos. Petit rappel rapide, le chaos engineering, c'est un sujet sur lequel aujourd'hui la communauté WeScale est en grand mouvement. On tenait à partager ces éléments auprès de la communauté française et internationale. C'est pour ça qu'on a organisé cet événement de la Chaos Week. Le but est bien sûr de vous soumettre des talks de qualité. Et on va attendre encore quelques minutes, car je vois que le créneau juste avant a été terminé. On va laisser quelques minutes aux personnes de nous rejoindre. On démarre dans 2 minutes. Bonsoir Akram. Nous allons commencer. Alors, le talk est en anglais. La présentation sera faite en anglais car la présentatrice ne parle pas français. So now let's switch to English. Okay. I will introduce the speaker. So as I told you, Yury Nino is working at the ADL Digital Lab. She is a technical program manager, site reliability engineer, and chaos engineering advocate. She loves to build software application, read blogs, and write articles. And let's welcome her right now.
Hi.
Hello.
Hi, everybody. Hi, Vino. Nice to meet you. So, can you see my screen?
Agathe, can you bring the screen? Okay. I will give you the lead, Yury, and I will take my leave. Have fun.
Okay. So when you say me, I can start. So I don't know if you are seeing my screen, but at this moment I am sharing it. Yeah. So let me know when I can start.
Yes, we are seeing your screen. You can start. So, sorry.
No problem. So I am going to start. Yeah. Sorry, I have to move to, okay. Hi everybody. Hi everybody. The title of my talk is Machine Learning to Predict Chaos. So nice to meet you. I am Yury Nino. I work as SRE Technical Program Manager in ADL Digital Labs, a company in Colombia that provides technology and innovation services. I am Colombian, so nice to meet you. And innovation services. So they are my contact data. You can find me in Twitter, LinkedIn, Medium as at Yury Nino, and it is my personal webpage if you want to know more about chaos engineering and know about our work in between the Spanish community. So in the next minutes, I am going to talk about two novel research areas that have demonstrated a big potential in the solution of specific problems. I am speaking about machine learning and chaos engineering. Those areas are shown a big progress in areas like medicine, transportation, software, education, and finances. To provide a context, I am going to start with a review of cloud-native transformation. For each one of those areas, I am talking about chaos engineering and machine learning, I am going to explore how those emerging paradigms can use chaos engineering to manage the pains in the path toward providing a digital solution. So finally, I am going to describe an example applying one of the methodologies of machine learning. Specifically, I am going to describe how to predict an operations failure of a taxonomy provided by Adrian Kovprof. So let me start talking about cloud-native transformation. I've listened this phrase lastly, that cloud native is the future of computing. It looks like it will save the planet. Everyone seems to agree on that. Another promises include it is going to allow you to deliver software more quickly or more cheaply. It brings together developers and operation people, ending years of discord, and it helps you delight your customers while pleasing your accounts and shareholders. That is a promise of cloud native. So in my opinion, cloud native is more than a tool set. It is a complete architecture. It is a philosophical approach for building applications that take full advantage of cloud computing. It is also complex both conceptually. Cloud native is an architecture for assembling all cloud-based components in a way that optimizes the cloud environment. It is not about the servers, but the services. So cloud native is also an organizational destination. The current goal for enterprises looking to modernize their infrastructure and processes, and given organizational culture. So why machine learning, artificial intelligence, and chaos engineering are important here? Since cloud native is still new and mysterious, so the cloud native maturity matrix could be useful for organizations that want to map the path between where they currently find and where they want to go. Once you start the journey toward cloud native, you will find that the future is based on artificial intelligence. If you see, that is the next step. Artificial intelligence-driven decisions and preventive machine learning and artificial intelligence. In the future, humans will be cut out on these processes. In the next generation of those systems, machine learning and artificial intelligence will handle operational and maintenance processes. Systems can learn on their own how to prevent failures by, for instance, automatically scaling up capacity. Let me one moment. So that is the reason for the context of cloud native. So it is the future. Humans are defining the starting point for machines to learn and constantly improve. Health healing, it is the optimal way to systems to be operated and maintained. It is faster, more secure, and more reliable. So let me move now to machine learning foundations. So what we want is a machine that can learn from experience. It is a phrase from Alan Turing, said in 1947. So how one define AI can vary greatly. There are a lot of definitions on the internet about artificial intelligence, machine learning, and data science. So I would like to clarify some context, these concepts. It is a definition that I like. Artificial intelligence is intelligence demonstrated by machines. A more formal definition says that artificial intelligence is an area of computer science that studies how machines can perform tasks that will normally require a sentient agent. The question here is that if we are going to trust in those machines for doing things such as driving a car, giving instructions in an airport, for example, or share a beer like in this photo, we need to trust in them. They must be reliable. Here, some definitions. Artificial intelligence sounds sexy, get us money. Its goal is to make human-like machines. Machine learning is a subset of artificial intelligence that makes machine learning from past data. And data science apply machine learning to create actual products. Data science deals with real-world complexity. They are definitions that we are going to need in order to understand another concepts in the next slides. Machine learning is an integral part of data scientists' approach to a problem. The rise of accessible machine learning has made it a present part of our technology ecosystems. At a fundamental level, machine learning is the process of writing an algorithm that can learn as consumes more data. It has driven the importance of having data scientists in every big company. Traditional definition says that machine learning is an application of artificial intelligence that gives computer systems the ability to learn from the data and improve from past failures and experience. While this definition gives us a sense of machine learning in very technical terms, it fails to give us a broad outlook of this potential and how it is relevant today. To conclude, machine learning is the future of knowing our doors. So let me share with you a classification of algorithms in machine learning. Machine learning problems can be broken in two types: supervised and unsupervised learning. Supervised learning defines problems where you know the ground truth label for your data in advance. You feed this label data to your model in hopes that it can learn enough to label new examples. With unsupervised learning here, with this type of learning, you don't know the labels for your data in advance. And the goal here is building a model that can find natural groupings of your data. This process is called clustering. Compress the information context. In other words, dimensional reduction, or find association rules. They are algorithms classified into types of schemes for machine learning. So because big data is important and machine learning is very important for our industry and academia at this moment, it is important in our daily life. Here are some applications for machine learning. Remember, data contains information. Information leads to insights, and insights help us in making better decisions. The application of supervised learning can be classified into groups: classification and regression. Amongst applications for classifying data, we can find image classification, customer retention, identity fraud detection, and disease diagnosis. In the same side, regression algorithms here, so which are used in the most cases for predicting things. Are used for advertising popularity prediction, weather forecasting, market forecasting, and population growth prediction. So, in my opinion, a more difficult type of learning, unsupervised learning, can be classified also into groups, dimensional reduction and clustering. The first one, dimensional reduction, is commonly used for meaningful comprehension, structure discovery, and big data visualization. So that is a resume or a review of those applications. To conclude, machine learning has a lot of applications in systems that we use daily. Healthcare industry, final service industry, social media, travel industry. They are all applications for machine learning. And here it is important to notice all those applications are susceptible of chaos. So I am going to move to chaos engineering concepts because they are applications for machine learning, but if you notice, they don't mention chaos engineering and they are susceptible of chaos. So let me talk more about chaos. It is the chaos theory. Many years ago, the pioneers of chaos theory said that the butterfly effect makes long-term prediction impossible. Even the smallest perturbations to a complex systems like weather or economy, for example, they are complex and dynamic systems, can concatenate the events that leads to a divergent future, unable to pin down the state of those systems precisely enough to predict how they will play out, because we live under of veil of chaos or uncertainty. So that is the theory for chaos, and they mention it that it is impossible to predict the chaos in dynamic and difficult systems like that economy and weather, for example. Regardless of that theory and complexity associated to the chaos, a group of researchers decided to challenge pioneers of chaos theory. So new findings come from chaos theories, Edward Ott and 4 collaborators at the University of Maryland. They employed a machine learning algorithm to learn the dynamics of an architectural chaotic. It is the 4 of them, the researchers, and they have shown that machine learning, it is a powerful tool for predicting chaos. In the next slides, I am going to explain a little more about it. Basically, after training a model with data from past evolution, they use a complex equation known Kuramoto-Zibachniski. My apologies if my pronunciation is not the better for the name of the algorithm, but I am going to share the slides after this presentation. So to predict chaos, they discovered that machine learning is very, very useful predicting chaos. We have a lot of challenge for that because we are facing failures in difficult and sophisticated systems, but it is possible. So Ott, the main researcher, and his colleagues achieved their results by synthesizing existing tools. 7 years ago, when a powerful algorithm known as deep learning was starting to master artificial intelligence tasks like image and speech recognition, they started reading on machine learning and thinking of clever ways to apply to chaos. They learned of a handful of promising results predicting the deep learning revolution. In the early 2000s, they made use of a network of randomly connected to artificial networks, which formed the base to learn the dynamics and the difficulty of those systems in 3 chaotical co-evolving variables. They started training the models with 3 series of numbers. The network predicted the future values of these three variables to impressively distant horizon. However, when there were more than a few interacting variables, the computations become impossible. Ott and his colleagues needed a more efficient scheme to make computer relevant for large chaotic systems, which have huge numbers in interrelated variables. Every position along the front and advancing flame, for example, I am going to take an example with a flame, for example, has velocity components in 3 spatial directions. So we have three variables to map the space. So to keep track of them. So Ott explained that the solution has 3 steps that can be used to predict the evolution of the chaos or the spread of flame, the fire, sorry. Remember, I am going to use an example using fire. So in the next slide, I am going to explain the process that demystified the chaos theory that says that the butterfly effect makes prediction for chaos impossible. The researchers showed that the predicted flame-like solution exactly matches the true solutions before chaos finally wins and the actual unpredicted states of the system diverge. So they are the steps I am going to explore one-on-one. So in the first step, you measure the height, the flame at 5 different points. Continue to measure the height at those points on the front as the flame advances over a period of time. You feed this data when you have a lot of data about the height, about the size of the flame. You feed this data to a model, to a machine learning model, randomly choose artificial neurons. So in this case, we are using an algorithm for machine learning known as neural networks. The input data triggers the networks to fire. So triggering connected networks into and sending a cascade of signals through the network. So in a second step, the idea is to make the neural network learn the dynamics of evolving flame from the input data. To do this, as you feed data in, you also monitor the signals of several randomly chosen neurons. Weighting and combining these signals in 5 different ways produce 5 numbers as outputs. So if you consider at the start, we have 3 numbers. And at this moment, as you feed the neural network, you had more information for future trainings. So the goal is to adjust the weights of various signals that into calculating the outputs until those outputs match the next set in outputs. It is an iterative process. So the 5 new heights measure a moment later along the frame front. To learn the correct weights, the algorithms compare each set of outputs or predicted the flame weights at each of the 5 points on the next set inputs, or actual flames height increasing or decreasing the weights of the signal each time. So let me move to a final step. The third step, you actually to do the prediction. So having learned the system dynamics can reveal how it will evolve, the neural network essentially asks itself what will happen. So outputs are feedback, it as new inputs. Whose outputs are feedback in an input as soon as making a projection of how the heights or the numbers at the 5 position of the flame from it will evolve. So that is an example for machine learning using a simple method to predict. That is trivial, no? Because that is really difficult to use, for example, a neural network. But the idea is to have 3 steps. Feed the model with input data, and train the network and predict about considering this information. So it is the taxonomy of failures defined by Adrian Koftov. He is an important person in the chaos engineering community, so which could be predicted using previous model. So as I mentioned, in the next generation of system, machine learning and artificial intelligence will handle operational and maintenance processes. So that is an application of those phrases. So systems can learn on their own how to prevent failures, but for instance, automatically scaling up capacity. So they are the framework. Failures are classified in 4 categories: operation, infrastructure, application, and software. And we can classify different incidents or different failures between these categories: insufficient observability, poor capacity planning, and inadequate incident management. They are examples for operations failures. And for infrastructure failures, we have device failures, internet failures, CPU, RAM, disk failures, and data center failures. And cascading failures, retry storms, bad configurations, and versioning. And finally, between the category for software, we have failures, common failures. Probably you were facing these failures in the past. Expiration certificates, revocation licenses, security exploits, runtime bugs, and language bugs. So our conclusion here is humans are defining machines to learn and constantly improve in order to avoid these failures. That is the idea, that is the purpose of chaos engineering. So here are some ideas to apply the odds models. Remember the main research? So here are some ideas to apply his algorithm and his technique to predict chaos. So for classifying operational failures, I choose operational failures, but these concepts can apply to any failures time. So for this step, we think we could identify and measure the characteristics of a failure. For example, are we using an observability tool such as Datadog, Grafana, or New Relic? Are we, do we have observability about SLOs? Are we following an incident management methodology? Are we writing postmortem? Did we practice game days? With this information, with these answers, we can fit a model in order to predict the chaos. Because, for example, if we are not using an observability tool, probably our incident there will be a big incident. So that is the data. That is the data for feeding the neural network model. So in a second step, we have to train the model. So in this step, we train the model. So we have to provide examples of previous projects. So some ideas here is, for example, if we don't use an observability tool, the response type is that you measure that what is the time when you are not using an observability tool. If we cannot follow SLOs in an observability tool, our KPIs are. And if we don't have an incident methodology, we are attending in the same way the incident. So that is that is a technique for training or for providing more information for our model. And finally, we have the possibility to predict the failures. So we can ask the neural network, I lost the access to observability tool. What will the impact in the responses times? If we write postmortems, how could improve my response times? And if I will invest X money at time in a game day, next month, what will my revenue, for example? And they are ideas to apply the chaos, apply the model in order to predict the chaos. So we train the model, we fit the model with information related to observability tool, incident management methodology, and numbers. And after that, we provide rules in order to train the model. What happened in the past when we don't have this tool, for example. And finally, with this information, the neural network has the capability to predict chaos, considering the algorithms designed for that. So what is the next challenge? I would like to start this part with this phrase: artificial intelligence is being used for providing resilience and reliability, but it is an artificial intelligence reliable and resilient because we explore how can we use machine learning for solving chaos engineering issues. But what happens in the other side? We can use chaos engineering in the artificial intelligence and machine learning models. The answer is yes. I have seen a lot of words and marketers saying that chaos engineering will soon pair with artificial intelligence and machine learning tools to help automate a lot of the analysis and recovery activities. They are designing a smart system that will be better at scanning networks and cloud environments to monitor performance and stability during tests. However, what about those machine learning systems that I mentioned? Are they reliable? Are they resilient? If we are going to trust in a car that has the possibility auto drive, we have to trust in the system. This system has to be resilient and reliable. Let me explore those in the next slides. We can start with big data, a form of artificial intelligence. Nowadays, at a high level, organizations are tuning to big data and analytic solutions to navigate the challenge that they are facing. Organizations are using big data to manage the customer experience, transform their products, and deliver digital services. Considering that those are many sides of the business, we need to ensure that this data is reliable. So, and again, chaos engineering is perfect here. If we need to guarantee reliability and we can't apply chaos engineering. So another big side of artificial intelligence is related to machine learning. But what is the learning? So learning is the acquisition of knowledge or skills through study, experience, and being taught, as I mentioned. So those robust machine learning systems and hardware architectures are required to generate reliable and trustworthy results in the presence of hardware-level faults, while also preventing security and privacy. And since computers exist, people have tried to teach them how to process human language works, but only recently, with this rise of new technologies and ever-increasing computing power, natural language processing has made its entry in our everyday life. Whether it is a device processing human speech, like Alexa, for example, Alexa from AWS, or written language, and how our machines are able to understand language and extract information from it. Computers are built to process structured numerical data, so the inconsistency and volatility of human language therefore turns natural language process into a complex data susceptible to fail. What makes processing language a very complex task? That needs a reliable technique to profit. Chaos engineering is a good option here. So the usual approach to predicting a chaotic system is to measure its conditions at one moment as accurately as possible. Use this data to calibrate a physical model and then evolve model toward. That is the same in the other side, the other application. So in artificial intelligence, chaos engineering is very useful to test models injecting failures. That is a conclusion. I think that is a great opportunity to evolve our knowledge and progress for an unexplored field, chaos and fusion. That is another topic I would like to deep on in another presentation. So the idea is attack architectures and models designed for artificial intelligence solutions are designed for machine learning implementation. For example, architectures based on Spark, that there is an architecture based on a cluster. You have a working node working for providing a solution. That is a perfect scenario to use chaos engineering, because when you inject a failure in those complex systems, you can have the possibility to test your system and to test the connections between these components. Test models, injecting failures, chaos and functions, that is another concept, that is a really interesting concept, and use artificial intelligence to classify postmortems. That is another application, using using artificial intelligence to classify postmortems in order to get more information about them and to have the possibility to classify in a reduced set of postmortems in order to manage an incident in the future. So failures, I would like to finish. I would like to close my presentation with this phrase. Failures are inevitable part of making software products and services, and artificial intelligence and machine learning topics are susceptible of chaos. That is a fact. So, however, it is not necessary to repeat the mistakes of the past. Although they are complex systems, dynamic systems, and very hard systems, and the theory says that is impossible to predict chaos, we have the first approaches, the first approximations in order to use artificial intelligence for solving chaos engineering issues, and use chaos engineering for manage the failures in an architecture for providing solutions for artificial intelligence and machine learning solutions. So we are here. Humans are defining the starting point for machines to learn and constantly improve. Self-healing is the optimal way for systems to be operated and maintained. It is faster, more secure, and more reliable. Systems learn on their own how to prevent failures by, for instance, automatically scale up capacity. There is a phrase, there is a part of text that I like, so I would like to remember you again. So finally, artificial intelligence is being used for providing resilience and reliability, but it is artificial intelligence reliable and resilience? That is an open question for you. So thank you very much. They are my thank you very much. They are my contact data. My personal webpage is www.yurynino.com. So at this moment we are working with the Spanish community in really interesting projects, include machine learning and artificial intelligence topics. And so we have a web page, when you can find more information about this. The page is Ingeniería del Caos in Spanish, ingenieriadelcaos.com. We have this web page with some interesting projects about that. So thank you very much. And if you have questions, let me know, please.
I was surveying the chat. For now, we don't have any question. Let's wait a few minutes.
Okay. I hope that they are novel concepts, can be useful for you.
Thank you for the presentation. It was really interesting.
Thank you. Oh, all is clear, or it is confused. But,
Akram confirms that it was a great talk and totally clear.
okay.
I think that's why we don't have any question. Well, I think it will be time to say goodbye. I don't think we'll have any question. So I'd like to thank you in the name of the team of the Chaos Week and the French community about chaos engineering for your presentation. It was really well explained and I think crystal clear. And stay safe.
Yeah, thank you very much. Take care of you and your family. I hope that we are living a difficult situation at this moment, but thank you very much. Yeah. Thank you very much. Have a good day, and thank you for this opportunity in order to share our approximations with chaos engineering and artificial intelligence and machine learning topics. Thank you very much. Have a great day. Bye.
Bye.